Hello everyone, I am Professor Sanjay Bhargav once again welcoming you to my YouTube channel Physics with Dr. Sanjay Bhargav. In this video on moving charges and magnetism part 3, we would be dealing with Amperes Circuital Law. We like to calculate magnetic field due to a current carrying conductor of infinite length. We would calculate magnetic field due to a solenoid and calculate magnetic field due to current carrying thick cylinder. We begin with Amperes Circuital Law. It says the line integration of a magnetic field around a closed path in vacuum is equal to mu 0 times the total current enclosed by the closed path. Mathematically, integration B dot dl must be equal to mu 0 I, or B dl cos theta must be equal to mu 0 I. So Amperes Circuital Law ये क्या बताता है कि magnetic field around a closed path in a vacuum is equal to mu 0 times the current that would be enclosed by the closed path. Here theta is the angle between the direction of magnetic field and dl. So B vector और dl vector के बीच में जो angle है उसको हमने theta assume किया है. This represents the integration taken round the closed loop. I is the current enclosed by the loop. So I represents the enclosed current and integration with a circle represents the integration along a closed loop. This loop is normally called as the Amperian loop. Like in Gauss law, we used to say as the Gaussian surface. Similarly here, we want to call it as the Amperian loop. Now, how do we apply Amperes law? So we'll deal with certain applications of Amperes law. The first application says magnetic field due to current carrying conductor of infinite length. So we want to calculate magnetic field due to current carrying conductor of infinite length. So here we have a straight conductor here carrying a current I. Whenever it carries a current I, then according to right hand rule, the magnetic field lines are concentric circles. The direction of the magnetic field at any point can be determined by drawing a tangent at that particular point. So we define our system as we consider a straight conductor carrying a current I. To calculate magnetic field at point P, we consider a closed loop of radius A. The circular loop is made of small elements of length dl. So one dl marked here. Now, what does the Amperes law say? Integration B dot dl must be equal to mu 0 times I, or integration B dl can be written as B dl cos theta. Since the angle between magnetic field and dl is 0, so theta is supposed to be 0, so cos 0 is supposed to be 1. So B integration dl must be equal to mu 0 times I, and integration dl is equal to the circumference. A is the radius of the circle, so it becomes 2 pi a. So magnetic field is equal to mu 0 I upon 2 pi a. So B is inversely proportional to A. And what is A? The distance of point of observation. The direction of the magnetic field is given by right hand rule. It says hold the wire in your right hand with thumb pointing in the direction of current. Then the fingers will curl in the direction of a magnetic field. अपने राइट हैंड से कंडक्टर को होल्ड करो इस तरीके से कि thumb points in the direction of current, then the direction of the curling fingers will give the directions of magnetic field. Now, what does the equation B is equal to mu 0 I upon 2 pi A show? The magnetic field due to a straight conductor depends on medium, that is nature of a medium surrounding the conductor, strength of the current flowing in the conductor, and distance of point of observation. So here B was proportional to I, here B was proportional to 1 upon A, and here B is directly proportional to mu. We can always draw a graph between B and A. Since B is inversely proportional to A, the graph comes out to be a rectangular hyperbola. As the value of A increases, the strength of magnetic field reduces. Magnetic field at every point on a circle of radius A is same in magnitude. That is, magnetic field is cylindrically symmetric. The direction of the magnetic field at any point of the circle is tangential to it. Thus, the line of constant magnitude of magnetic field form concentric circles. Thus, magnetic field lines form closed loops. These are very different to the electrostatic field lines which start from the positive charge and end at the negative charge. तो इलेक्ट्रोस्टैटिक्स में जो इलेक्ट्रिक फील्ड लाइंस आते थे वो पॉजिटिव चार्ज से शुरू होते थे और नेगेटिव चार्ज पर खत्म होते थे, जबकि मैग्नेटिक फील्ड लाइंस दे आर इन द फॉर्म ऑफ क्लोज्ड लूप्स. नाउ वी हैव सम थिंग्स हियर. नोट, Ampere's law for the magnetic field is analogous with the Gauss law for electric fields. जो काम आपके लिए गॉस लॉ करता था इलेक्ट्रिक फील्ड कैलकुलेशन का, वही काम हमारे लिए एम्पियर्स लॉ करता है मैग्नेटिक फील्ड के कैलकुलेशन का. गॉस लॉ was used to find electric field of the charge distribution with high symmetry. Similarly, Ampere's law is used to find magnetic field due to current distribution having a symmetry. गॉस लॉ क्या करता था? हाईली सिमेट्रिक चार्ज डिस्ट्रीब्यूशन, अर्थात जिन चार्ज डिस्ट्रीब्यूशन में सिमेट्री होती थी, चाहे वन डायमेंशनल हो, चाहे टू डायमेंशनल हो, चाहे थ्री डायमेंशनल हो, उनके इलेक्ट्रिक फील्ड को कैलकुलेट करने का काम करता था. इसी तरह से एम्पियर्स लॉ भी उन करंट डिस्ट्रीब्यूशन जिसमें सिमेट्री होती है उनका मैग्नेटिक फील्ड मालूम करने के लिए हम यूज करते हैं. एम्पियर्स लॉ involves a line integral around a closed path, while Gauss law involves a surface integral over a closed surface. Amperes circuital law holds for steady currents which do not change with the time. So, if the value of the current changes with the time, you cannot apply Amperes law. It is applicable only for the steady currents whose value does not change with respect to time. Second, Ampere's law bears same relationship with Biot-Savart's law as Coulomb's law bears to Gauss law. जिस तरह से Coulomb's law Gauss law के साथ एक रिलेशनशिप रखता था, उसी तरह से Ampere's law भी Biot-Savart's law के साथ एक रिलेशनशिप रखता है. अब सेकेंड एप्लीकेशन में हम मैग्नेटिक फील्ड कैलकुलेट करेंगे ड्यू टू अ सोलेनॉइड. A solenoid consists of a long wire wound in the form of helix where the neighboring turns are closely spaced. The net magnetic field is the vector sum of fields due to all the turns. Enameled wire are used for winding so that turns are insulated from each other. सोलेनॉइड किसका बना हुआ होता है? एक वायर है जिसको हम हेलिकल फॉर्म में टर्न करके हेलिक्स बना देते हैं. सारे के सारे टर्न्स एक दूसरे के साथ बहुत पास होते हैं. द नेट मैग्नेटिक फील्ड, हर एक सर्कुलर टर्न के कारण जो मैग्नेटिक फील्ड प्रोड्यूस होता है, नेट मैग्नेटिक फील्ड उसके वेक्टर सम के बराबर होता है। यहां पर टर्न्स या वाइंडिंग करने के लिए हम इनेमल्ड वायर्स लेते हैं। क्यों लेते हैं? सो दैट ऑल वायर्स आर इंसुलेटेड फ्रॉम ईच अदर। तो यहां पर these are the windings of solenoid. The figure shows the magnetic field lines for a finite solenoid. तो मैग्नेटिक फील्ड हमेशा एक्सिस के अलोंग होता है। सोलोनॉइड के बाहर मैग्नेटिक फील्ड नेग्लिजिबल है। तो यहां पर हम कह सकते हैं कि ये जो फिगर बी है, ये क्या बताता है? It shows that the field at the interior midpoint P is uniform, strong and along the axis of solenoid. इसीलिए हम नॉर्मली इलेक्ट्रिक मैग्नेटिक फील्ड ऑफ द सोलेनॉइड को उसकी एक्सिस के अलोंग मानते हैं। द फील्ड एट द एक्सटीरियर मिड पॉइंट Q इज वीक एंड इज अलोंग द एक्सिस ऑफ सोलेनॉइड विद नो परपेंडिकुलर कंपोनेंट। तो यहां पर आप देख भी सकते हैं कि जितने भी फील्ड लाइंस हैं, देखिए ये सब एक्सिस के अलोंग हैं और ये सब लगभग एक ही डायरेक्शन में हैं। बाहर वाले पॉइंट पर यहाँ पर अगर आप टेंजेंट ड्रॉ करेंगे तो टेंजेंट इस तरह से आएगा, विच वुड बी ऑपोजिट इन डायरेक्शन विद रिस्पेक्ट टू द एक्सियल फील्ड लाइंस। तो जो भी फील्ड लाइंस आएंगी, चाहे अंदर आए चाहे बाहर आए, दे आर अलोंग द एक्सिस और वहां पर कोई परपेंडिकुलर कंपोनेंट देखने को नहीं मिलता है। According to this figure, the field outside the solenoid approaches zero. The field inside becomes everywhere parallel to the axis. यहां पर हमने बोला है कि we consider a rectangular Amperian loop ABCD of length h. Let us see in the figure. तो ये एक एम्पीरियन लूप है, ए, बी, सी और डी। ठीक है ना, रेक्टेंगुलर लूप है जिसकी लेंथ आपने एच रख रखी है। ए बी इज पैरेलल टू द मैग्नेटिक फील्ड, थीटा एंगल कम्स आउट टू बी 0. सो हियर वी हैव रिटन लेट n बी द नंबर ऑफ टर्न्स पर यूनिट लेंथ, देन द टोटल नंबर ऑफ टर्न्स इन द सोलेनॉइड इज n times h. I is the current through solenoid. According to Amperes law, integration along the closed path, that is ABCD, and back to A, is equal to mu 0 times Ni. Now integration B dot dl along ABCDA is equal to integration from A to B, B to C, C to D and D to A. And when it says B dot dl A to B, theta is 0, so cos 0 is 1. From B to C, theta is 90, cos 90 would be 0. Here theta is 0 in DC, and therefore because it lies outside the solenoid, and from D to A, theta is equal to 90, cos 90 would be 0. So out of 4 integrations, the 3 integrations vanish. So integration B dot dl is equal to B integration A to B dl, which would be equal to B times h. B times h is equal to mu 0 Ni, or B would be equal to mu 0 N upon h into I, that is mu 0 Ni. N is the number of turns per unit length. The direction of the magnetic field is once again given by the right hand rule. The solenoid is used to obtain a uniform magnetic field. The direction of the magnetic field is along the axis of solenoid. So solenoid में magnetic field का direction क्या आता है? Direction हम determine करते हैं right hand rule से. Solenoid uniform magnetic field बनाता है और उस field का direction हमेशा axis of the solenoid के along होता है. The magnetic field due to solenoid depends on number of turns in the solenoid, length of the solenoid, nature of medium inside the solenoid and strength of the current. So यहाँ पर B proportional to I, यहाँ पर B is proportional to mu and यहाँ पर small n was equal to number of turns per unit length. So it depends on number of turns also, and it depends on length of the solenoid also. Now, as the third application to Amperes law, we would like to calculate magnetic field due to current carrying thick cylinder. So here we assume a solid cylinder of radius r carrying a steady current I. The current flows through the entire cross-sectional area. The current density at every point is taken to be uniform. So current density, we define it as total current upon total area. So here this represents a conductor, this represents the cross section. So here this is the central point O. How do I calculate the current density? It is defined as current per unit area. R is the radius of the conductor. So pi r square is the area of cross section. Now we need to calculate magnetic field at an external point, magnetic field at a point on the surface, and at a point inside the conductor. First we like to calculate magnetic field at an external point P0 where R0 is greater than R. So O P0 is equal to R0, which is greater than R. Now from Amperes law, integration B dot dl must be equal to mu 0 times the sum of current enclosed. B dot dl cos theta must be equal to mu 0 summation I. In our case, theta is supposed to be 0, so cos 0 would be 1. B can be replaced by B0 and summation I is the total current I. So we can write B0 integration from 0 say 2 pi R0 dl must be equal to mu 0 I. So integration dl equal to the circumference. So B0 2 pi R0 must be equal to mu 0 times I. So B0 is equal to mu 0 into I upon 2 pi R0. So B0 is directly proportional to 1 upon R0. Now we would like to calculate at the surface of the conductor. At the surface of the conductor, R is equal to R. So in our earlier equation, replace R0 by R. So I get magnetic field at the surface would be mu 0 I upon 2 pi R. Now important part is magnetic field at internal point Pi. Let us calculate at an internal point where Ri is less than R. As per the Amperes law, integration B dot dl must be mu 0 times the sum of currents. So integration B dot dl cos theta mu 0 times the summation of current. So theta is equal to 0, B would be equal to Bi, summation I would be equal to. So how do we imagine? This represents a conductor of radius R. In this conductor, we are assuming a small section through which the current is made to pass. So we are interested in the current passing through this internal part of the conductor. So we calculate summation I, current density into area of cross section of the internal section, that is pi into Ri ka square. Rho was equal to I upon pi R square. So the current that would be enclosed inside the part would be I into Ri ka square upon R square. So Bi integration 0 say 2 pi Ri dl would be equal to mu 0 I Ri ka square upon R square. So we can cancel here Ri with Ri, and what we get is magnetic field Bi would be equal to mu 0 capital I upon 2 pi R square into Ri. So Bi is directly proportional to Ri. At the center of cylinder, Ri would be equal to 0. So B at the center is also 0. An important result which says magnetic field at the center of the conductor is 0. कंडक्टर के सेंटर पर मैग्नेटिक फील्ड की वैल्यू 0 आ जाती है. हम इन सभी रिजल्ट्स को एक ग्राफ में प्लॉट कर सकते हैं. सो वी हैव रिटन द वेरिएशन ऑफ मैग्नेटिक फील्ड विद डिस्टेंस r फ्रॉम द सेंटर ऑफ द वायर इज प्लॉटेड एज. देखिए यहाँ पर this point represents the point on the surface, so magnetic field at the surface is maximum and is equal to mu 0 I upon 2 pi r. In the internal side, bi is directly proportional to ri, so the graph must come out to be a straight line. So from point O to the surface point S, we can say bi is proportional to ri when r is less than r. As you move away from the center to the circumference or the surface, the magnetic field keeps on increasing. At the surface, it becomes maximum, and outside, B0 is proportional to 1 upon R0. So I can be allowed to write that the graph would be an rectangular hyperbola. As the distance from the center increases, the strength of the magnetic field also decreases. So this graph completely represents the behavior of a magnetic field when the current is made to pass through a thick cylinder. Now let us try to understand with certain examples what we have learnt with the help of Amperes law. Example 1. A solenoid coil of 300 turns per meter is carrying a current of 5 ampere. The length of the solenoid is 0.5 meter and has a radius of 1 centimeter. Find the magnitude of magnetic field inside the solenoid. So strength of the solenoid, magnetic field inside the solenoid, B is equal to mu 0 Ni. Small n represents number of turns per unit length, and that is given as 300 turns per meter. I is given as 5 ampere. Mu 0 is 4 pi into 10 raised to power minus 7, n is written as 300 and the current is 5. So strength of the magnetic field is 1.9 into 10 raised to power minus 3 Tesla. In example 2, let us pick up. It says a wire of radius 0.5 centimeter carries a current of 100 ampere, which is uniformly distributed over its cross section. Find the magnetic field at 0.1 centimeter from the axis of the wire, at the surface of the wire, and at a point outside the wire 0.2 centimeter from the surface of the wire. So when I say magnetic field inside, the relation says mu 0 I upon 2 pi r square into ri. So it would be 4 pi into 10 raised to power minus 7. The strength of the current is 100 and the distance ri is 0.1 centimeter. So 0.1 into 10 raised to power minus 2 meter upon 2 pi, and the radius is given as 0.5 into 10 raised to power minus 2 or uska whole square. The calculation gives me the strength of the magnetic field inside as 8.0 into 10 raised to power minus 4 Tesla. Can be written as 0.8 into 10 raised to power minus 5 Tesla. Now what I do is I need to calculate magnetic field at a surface point given by the relation mu 0 I upon 2 pi r. Mu 0 is 4 pi into 10 raised to power minus 7, I is 100, 2 pi and r is 0.5 into 10 raised to power minus 2, that is 4 into 10 raised to power minus 5 Tesla. So magnetic field at the surface is a maximum, and outside it decreases from 4 according to the distance as given in the question. So outside B would be equal to mu 0 I upon 2 pi r0, 4 pi into 10 raised to power minus 7 into 100 the strength of current, 2 pi and r0 is 0.7, 0.5 is the radius and 0.2 is the external distance of the external point. So 0.7 into 10 raised to power minus 2, and it gives me 2.86 into 10 raised to power minus 5 Tesla. Example 3. Let us pick up example 3. It says a 0.5 meter long solenoid has 500 turns and has a flux density of 2.52 into 10 raised to power minus 3 Tesla at its center. Find the current in a solenoid given mu 0 as 4 pi into 10 raised to power minus 7 Henry per meter. Now what would be the number of turns per unit length? Total number of turns 500 and total length 0.5. So it would be 1000 turns per meter. Now for a solenoid, B is equal to mu 0 Ni. So I would be equal to B upon mu 0 N. B is 2.52 into 10 raised to power minus 2 Tesla. Mu 0 is 4 pi into 10 raised to power minus 7 and small n is 10 raised to power 3. So it would be 2 ampere. Example 4. A long straight wire carrying a current of 30 ampere is placed in an external uniform magnetic field of 4 into 10 raised to power minus 4 Tesla parallel to the current. Find the magnitude of resultant magnetic field at a point 2.0 centimeter away from the wire. So magnetic field due to a straight conductor is mu 0 I upon 2 pi r. So it is 4 pi into 10 raised to power minus 7 into 30 upon 2 pi, and the r is given as 2 centimeter, that is 2 into 10 raised to power minus 2 meter. So the magnetic field due to a straight wire would be 3 into 10 raised to power minus 4 Tesla. This field will act perpendicular to the external field, which is B2, 4.0 into 10 raised to power minus 4 Tesla. So what would be the resultant field? It would be under root of B1 ka square plus B2 ka square. B1 is 3 into 10 raised to power minus 4 ka square, and B2 is 4 into 10 raised to power minus 4 ka whole square. It gives me 5 into 10 raised to power minus 4 Tesla. Now we pick up example number 5. Two parallel wires P and Q placed at a separation R is equal to 6 centimeter carry electric current I1 is equal to 5 ampere and I2 is equal to 2 ampere in opposite directions. Find the point. Note. So let us choose the 2 points P and Q. Let the point where magnetic field is 0 be R at a distance x. At the required point, the resultant magnetic field due to two wires will be equal in magnitude and opposite in direction. Such a point will be either to the left of P or right of Q. Since I2 is less than I1, so point lies closer to the point Q. Right? So that is how we select on the basis of the strength of the current. Because point can exist either to the left of P this way, or it can be on the right of I2. How to select? I2 is less than I1, so the point lies closer to point Q. Let this point be R at a distance x from point Q. Field due to I1 at R would be equal to mu 0 I1 upon 2 pi R plus x normally into the plane of a paper. Field due to the strength I2 of the current at point R, B2 would be equal to mu 0 I2 upon 2 pi x normally out of the plane of paper. B1 and B2 both are equal in magnitude. So I can write mu 0 I1 upon 2 pi R plus x must be equal to mu 0 I2 upon 2 pi x, or I1 upon R plus x must be equal to I2 upon x. So I1x is equal to I2R plus I2x by cross multiplication. I1 minus I2 into x must be equal to I2 times R. So I can calculate x, it must be equal to I2 upon I1 minus I2 into R. Substituting I1, I2 and R, we get x as 4 centimeter. So the point lies at a distance of 4 centimeter from the point Q. Now example number 6. Find the magnitude of magnetic induction at the midpoint O due to current arrangement as shown in the figure. Current in these are the two conductors of this shape. You need to calculate what would be the magnetic field at point P. Now current in AB and ED, this is AB and ED, will not generate any magnetic field at O. Magnetic field at O due to current BC and ET are outwards. So due to current in the upward direction, the magnetic field is perpendicular to the plane of the paper and outward. Similarly, due to BC, the direction of the magnetic field is perpendicular to the plane of the paper and outwards. So what we can do is, we can just calculate the magnetic field due to straight conductor. It would be mu 0 of I upon 4 pi R, and R is A by 2 in both the cases. So the net magnetic field comes out to be mu 0 I upon pi A. Hope this video completely explains you about Amperes Circuital Law and its application. If you are learning physics from these videos, we just request you to like and comment on our video. Also subscribe our channel so that you can receive notifications of new videos in time. Thank you very much.